Imagine a rocket ship. You climb inside. Engines begin humming. Coordinates set nowhere. Any direction works. Forward into darkness. Then you accelerate. Past the moon. Past distant planets. Beyond the sun. The solar system fades. Stars surround you slowly. Years drift quietly. Then centuries pass. Millions of years. Then billions more. Still moving forward. Still crossing space. Galaxies slide past. Clusters fade behind. Blackness stretches ahead. And eventually, a question appears. A simple question, almost childish sounding. Where does it end? Does space stop somewhere? Is there a final place? A boundary waiting ahead? A cosmic wall, perhaps? A barrier across existence? Maybe a warning sign? End of universe. No further travel. Turn your ship. Return immediately. It sounds reasonable. Almost obvious, actually. Everything we know has edges somewhere. Rooms have walls. Countries have borders. Islands meet oceans. Even oceans meet land. Walk far enough, something stops you. Some limit appears. So naturally we wonder, where does space stop? According to Richard Feynman, questions can deceive us. Not intentionally, of course, but quietly, subtly. The trouble hides inside our imagination, inside the picture we carry inside. We imagine space as a giant container, a massive invisible box, stars floating inside, galaxies drifting slowly, everything contained neatly. And somewhere outside, something else exists. Perhaps empty darkness, perhaps another universe, perhaps absolute nothingness. But Feynman warned students, be careful with pictures. Human intuition evolved for forests and rivers, for hills and caves, for survival on Earth, not cosmic geometry, not curved spacetime, not the structure of the entire universe. So when we imagine space inside something, we may already be making mistakes. Long before physics, people noticed trouble. More than 2 millennia ago, ancient Greek thinkers debated the universe. They asked difficult questions. One philosopher proposed a clever argument. His name was Archytas, a mathematician and philosopher. His question was elegant, simple, and brutal. Walk to the edge, stand at the boundary. Now stretch your arm, push your hand outward. What happens next? 2 possibilities exist. Either your hand continues or something blocks it. Suppose it continues. Your hand moves freely. Then clearly that was not the edge. Space continues further. More universe exists. Now consider the alternative. Your hand stops abruptly. Something blocks movement. A barrier appears. Some final wall. But think carefully. That wall must exist. And anything existing occupies some place, which means again, space continues beyond. Either way, the boundary disappears. Every attempt fails. The edge retreats forever. 2,000 years ago, this simple reasoning revealed a strange truth. The universe resists boundaries. But centuries later, another puzzle appeared. A puzzle involving darkness. Step outside tonight. Look carefully upward. Observe the night sky. What do you see? Mostly empty darkness. A few scattered stars. Occasional distant planets. Perhaps the moon glowing. But mostly darkness. At first glance, nothing feels strange. Night should be dark. Darkness feels natural. But physics disagrees. A serious problem appeared. In the 19th century, astronomers noticed something, a logical contradiction, later named Olber's paradox. The reasoning is ruthless. Imagine an infinite universe, space extending forever, stars scattered everywhere, uniform in all directions. Now choose any direction, point randomly upward, follow that line through endless space. Eventually, it must hit a star, maybe extremely distant, maybe unimaginably distant, but eventually a star appears.
Now repeat again. Another random direction. Again, eventually, another star appears. Repeat infinitely many times. Every direction ends on a stellar surface, which means, logically, the sky glows everywhere. Not dimly either. Blinding stellar brightness. Every tiny patch as bright as a star itself. Night becomes impossible. Darkness should not exist. Yet reality contradicts it. The sky remains dark. Something must be wrong. At least one assumption must break somewhere. Maybe space finite. Maybe stars sparse. Maybe time limited. For many decades, nobody knew the answer. Then modern cosmology revealed something astonishing. The universe has age. It began long ago, roughly 13 billion years. The event called Big Bang. Because light travels with finite speed, a limit exists, a visibility horizon. Light from beyond has not arrived yet. Distant stars may exist but remain invisible, their light still traveling. The universe simply has not waited long enough. A second discovery followed. Space itself expands. Galaxies drift apart slowly, not through space, but with space, like dots painted on stretching rubber. This stretching changes light. Wavelengths grow longer. Blue becomes red. Red becomes infrared. Eventually, microwave radiation. Astronomers detected it with sensitive instruments. A faint cosmic glow, the leftover heat of the young universe. Scientists call it cosmic microwave background, discovered accidentally by Arno Penzias and Robert Wilson. They searched for noise. Instead, they found history. The earliest light still filling space, a whisper from creation. And suddenly, the dark sky made perfect sense. But solving darkness did not answer everything. One deeper mystery remained. If the universe expands, where does it expand? Into what exactly? Does space continue forever? Or does it curve and wrap around itself? Could the universe be finite, yet have no edge? That strange idea is where physics leads, and understanding it requires something extraordinary, a new picture of space, a geometry beyond intuition, a universe without walls. The mystery deepens. The sky is dark. The universe expands. Light travels slowly. These ideas explain the darkness above, but they leave another question alive. What shape is space? Is it endless flatness, stretching forever outward? Or something stranger, something curved, something closed? According to Richard Feynman, nature often surprises us, because our intuition expects simple geometry, flat floors, straight lines, parallel paths forever. But the universe does not promise simple geometry. To understand this, consider something familiar:
The surface of Earth. Stand anywhere. Begin walking forward. Choose any direction. North, south, east. Keep walking steadily. Days pass quietly. Weeks slowly fade. Months become years. Eventually, something strange. You arrive back home. The journey ends exactly where it began. Yet during travel, no edge appeared. No cliff emerged. No boundary stopped you. The Earth's surface is clearly finite, yet it has no edge anywhere. The secret is curvature. The surface curves through higher space, and this curvature removes the boundary. Now imagine something stranger. Suppose space itself behaves similarly. Not 2 dimensions, but 3 dimensions, a curved cosmic geometry. This idea emerged in the 20th century, when Albert Einstein transformed physics forever. His theory, called General Relativity. According to Einstein, gravity is not a pulling force. Instead, something deeper. Mass bends space-time. Stars curve space. Planets curve space. Galaxies curve space. Even light bends, traveling through curved geometry. This bending was tested during a famous eclipse.
In 1919, British astronomer Arthur Eddington observed starlight bending passing near the Sun. Exactly as Einstein predicted. Space was not flat. It was flexible. It could stretch. It could curve. Once physicists accepted curved spacetime, a new possibility appeared. The universe itself might also curve, not locally only, but globally too. Imagine again our rocket ship. You launch forward, crossing distant galaxies, always flying straight, never turning course. Years become centuries. Centuries become millennia. Your instruments remain steady, your engines constant. Nothing blocks your path. No cosmic barrier, no final wall. But something curious happens. The galaxies ahead begin shifting slightly. Distances behave strangely. Paths slowly converge. Space gently funnels. You keep flying onward. More time passes. Millions of years. Then something impossible appears. Familiar constellations return. Recognizable galaxies reappear. The sky looks familiar. Suspiciously familiar. Then realization strikes. You completed a loop. Your rocket circled the entire universe, arriving where the journey began. No boundary encountered, no edge discovered, yet the universe was still finite, exactly like Earth, a closed geometry, without boundaries. This idea fascinated physicists, a cosmic sphere, but in 3 dimensions, sometimes called a 3-sphere universe, finite in size, but edge-free. However, science demands evidence, not imagination. So cosmologists searched for measurements, clues hidden inside ancient cosmic light. Remember the faint glow? The relic radiation? The cosmic background? Scientists studied it carefully. Tiny temperature patterns appear, ripples from early universe, frozen in microwave light. Their apparent size reveals cosmic geometry. If space curves inward, patterns appear larger. If space curves outward, patterns appear smaller. But if space is perfectly flat, patterns appear exact. Satellites measured carefully. First came WMAP, then later Planck satellite. Their observations agreed. The result surprised everyone. Space appears flat, extremely close to flat, within tiny uncertainty. almost perfectly balanced, neither strongly curved nor dramatically closed, just nearly flat geometry. This discovery raised another surprising idea. Flat does not always mean infinite. Geometry and topology are different questions. Geometry describes curvature. Topology describes connections. And topology allows strange possibilities. A universe could be flat locally, yet finite globally. Imagine a video game, old arcade machines, spaceships crossing screens. Leave the right edge, reappear on the left. Leave the top, return from below. The screen feels endless, yet clearly finite. The trick lies in connected boundaries. Mathematicians call it a torus geometry. In 3 dimensions, a 3-torus universe. Perfectly flat locally, finite overall volume. But again, no edge anywhere. Travel long enough and paths repeat. Objects eventually return. The universe wraps around, like a cosmic maze. Physicists searched carefully for signs of repetition, identical galaxy patterns, matching circles of radiation, signals crossing the sky twice. So far, nothing confirmed. If the universe wraps around itself, the scale must exceed our observable horizon, beyond observable space, hidden beyond detection. Which leaves us with remarkable possibilities. Space may stretch forever, an infinite expanse. Or space may close upon itself gently, finite but edgeless. Either possibility works, but both share one surprising truth. There is no wall, no cosmic boundary, no edge waiting. And the deeper reason appears in physics itself, because an edge would create problems, serious physical problems, problems with symmetry, problems with conservation, problems with motion. Understanding that takes us deeper into fundamental laws and reveals why the universe almost certainly has no boundary at all.
The idea seems simple. A universe with edges, a cosmic boundary somewhere, a final barrier, a wall of existence. But physics becomes uncomfortable when boundaries appear, because boundaries introduce deep theoretical problems. According to Richard Feynman, nature prefers simplicity. Not human simplicity, but mathematical consistency. Equations must agree everywhere. Laws must work everywhere. No special exceptions allowed. If the universe had an edge, physics would suddenly change at that location, and that creates trouble. Imagine traveling outward, your rocket approaching the supposed boundary. Everything behaves normally. Gravity still works, light still travels, energy still moves. Then suddenly, a final surface appears. What happens there? Does matter bounce back? Does light reflect? Does time continue? Or does everything stop? Every option creates paradoxes. Consider a simple example. A beam of light, traveling toward the edge. When it arrives, something must occur. Either the light stops, or it reflects backward, or it passes through. Each option fails. If light stops, energy disappears mysteriously. Energy cannot simply vanish. Physics forbids that. If light reflects, what exactly reflects it? A cosmic mirror? A universal wall? Then that wall must possess structure. Atoms, perhaps, or unknown particles. But if structure exists, it occupies space, which means again, space continues beyond. The boundary collapses again. Now imagine instead light passes through the supposed edge, into something outside. But if outside exists, then the universe clearly continues there. Again, the boundary vanishes. Every logical path destroys the edge, and deeper physics reveals another reason, one involving symmetry, one of the most powerful ideas in science. Symmetry means laws remain identical in every direction, in every location, in every moment. If you perform experiments here on Earth or inside distant galaxies, the same physics appears. Gravity behaves the same, electrons behave the same, light behaves the same. This uniformity is not accidental. It connects directly to conservation laws, the connection discovered by Emmy Noether, a brilliant mathematician. Her theorem changed physics forever. Noether's theorem revealed something profound. Every symmetry creates a conservation law. Time symmetry creates energy conservation, spatial symmetry creates momentum conservation, rotational symmetry creates angular momentum conservation. These conservation laws govern everything, from falling apples to exploding stars, from orbiting planets to colliding galaxies. Now imagine again a universe with edges. Near the boundary, space suddenly ends. That location becomes special, different from everywhere else. Symmetry breaks instantly. And once symmetry breaks, conservation laws weaken. Energy might behave differently, momentum might change, angular momentum might vanish. Physics becomes inconsistent. But experiments show remarkable consistency everywhere. Light from distant galaxies obeys the same equations. Atomic spectra match perfectly across billions of light years. The universe behaves as if laws never change anywhere, which strongly suggests no special locations exist, no cosmic edges exist. Another argument emerges from relativity itself. Einstein's theory treats space and time together, a four-dimensional structure called spacetime. Inside general relativity, boundaries behave strangely. Edges create singular conditions. Mathematical inconsistencies appear. Field equations struggle to remain well-defined. To avoid these issues, cosmologists usually assume a boundary-free universe. Spacetime simply continues, either infinitely outward or curved back inward, but never abruptly ending. Even modern cosmology follows this assumption. The most successful model, called Lambda CDM model, it describes cosmic expansion, dark matter behavior, dark energy influence, galaxy formation history. And inside this framework, the universe possesses no physical edge. Observations support this. Astronomers scan deeper, using powerful telescopes. For example, Hubble Space Telescope revealed thousands of galaxies in a tiny sky region. Later, even deeper, images appeared captured by James Webb Space Telescope. Each deeper observation reveals more galaxies, more structure, more ancient light. Never a boundary, never a cosmic wall. Instead, space continues, further and further outward. But there remains an important distinction between observable universe and total universe. Because light travels with limited speed, we see only a spherical region, about 46 billion light-years radius. This region is called the observable universe. Everything beyond remains currently invisible, not because it ends, but because its light has not reached us yet. Physics suggests more universe exists, perhaps vastly more, maybe infinite in extent, maybe curved and closed, but either possibility removes the edge entirely. And here the mystery returns once again. If the universe has no boundary and no outer wall, what exactly is the universe expanding into? That final question puzzled physicists deeply, and the answer is stranger than expected, because space may not expand into anything at all.
The final mystery remains. A strange question, a deeply confusing one. If the universe expands, what lies outside? What surrounds everything? Where does expansion go? According to Richard Feynman, sometimes the difficulty comes from language itself. We ask the question using everyday intuition, but everyday intuition comes from small spaces, rooms and landscapes, boxes and containers. Whenever something expands in ordinary life, it expands into something. A balloon expands into surrounding air. A gas expands inside a chamber. An explosion expands through empty space. But the universe is not inside anything. It is not a balloon floating in darkness. It is not a bubble inside a larger void. The universe contains all space itself. So asking what lies outside becomes meaningless, because outside does not exist. Everything that exists is already included. To understand this, cosmologists often use a famous analogy. Imagine the surface of a balloon, small dots drawn across its rubber. Each dot represents a distant galaxy. Now, slowly inflate the balloon surface. Watch the dots carefully. Every dot moves away. All distances increase. No dot sits at the center. Expansion happens everywhere. Every location observes the same recession. Yet notice something. The surface itself has no edge. Travel across it and you never reach a boundary. But the surface still expands. Area continuously grows. Distances steadily increase, without expanding into the surface itself. Instead, the surface is stretching internally. Cosmologists borrow this simple analogy to describe expansion. But the true universe is more complex, not 2 dimensions, but 3 dimensions, space stretching everywhere, distances between galaxies slowly increasing. This discovery happened in the 20th century through careful observations by Edwin Hubble. Studying distant galaxies, he noticed something remarkable. Almost every galaxy moves away from us, and the farther a galaxy lies, the faster it recedes. This relationship became known as Hubble's law, which revealed something profound. The universe expands. Not galaxies flying outward, but space stretching, even empty regions slowly expanding. Later measurements refined the picture using satellites like WMAP and Planck satellite. Their observations showed expansion accelerating, driven by mysterious energy. Physicists call it dark energy, an invisible component dominating cosmic evolution, pushing galaxies apart, stretching space-time itself. And this expansion creates another horizon, a boundary not physical, but observational. Because space expands, some galaxies recede faster than light relative to us. Their light will never reach Earth, not because light breaks cosmic speed limits, but because space between us grows faster than photons travel. This defines the observable universe, a region roughly 90 billion light-years across today. Beyond that horizon, more galaxies exist, more cosmic structure, more unseen universe, possibly infinitely more. Or perhaps space eventually curves upon itself, a gigantic cosmic loop. Physics cannot yet decide. Current measurements suggest nearly perfect flatness, but slight curvature could still exist, hidden beyond detection. Future observations may reveal clues through precise measurements of cosmic structure using advanced telescopes. For example, James Webb Space Telescope studies early galaxies, mapping ancient cosmic history, while other missions search for subtle signals, tiny distortions in cosmic radiation, all attempting to answer one question: what is the shape of the entire universe? Infinite flat space or finite curved cosmos? Yet in both cases, one conclusion remains. There is no edge, no cosmic cliff, no boundary wall, no place where space suddenly ends. Instead, the universe behaves more elegantly, either infinite, outward, or closed without boundary. And this realization changes how we think about existence itself, because the universe is not inside some larger container, it is the container. Space is not inside the universe, space is the universe. And when it expands everywhere, at every location, at every moment. No center exists, no outer boundary exists, only geometry evolving. According to Feynman, this is often how nature behaves. The deeper answer removes the question. The universe does not expand into anything because there is nowhere else for it to go.